Hello students, today we are going to see the Laplacian operator. So it is nothing but first we have to take del dot del. Two times the del vector has to be enter into dot product. It is then multiplied with either with a scalar or vector. So del dot del will give a scalar quantity. After that, if this scalar operates on scalar, you need a scalar result. If this del dot del scalar quantity act on the vector, then it will result in vector quantity. So we know what is del, which is I into dou by dou x plus j into dou by dou y plus k into dou by dou z. We should be dotted with another del vector followed by the multiplication of this quantity u. U may be scalar or vector. So when these two have a dotted product, you get the answer del square, dou square by dou x square plus dou square by dou y square plus dou square by dou z square, and this bracket is a scalar quantity. Then you multiply with the u, which is here at present it is a scalar, it may be a vector also. If you multiply u with this, once again you get a scalar. If you multiply with a vector, you get a resultant as vector quantity. What does the Laplacian physically means? So as a second derivative, because it is a second derivative, Laplace equation is a second derivative equation. The one dimensional Laplacian operator is related to minima or maximum, either whether it is a minimum or maximum. Whereas the second derivative is positive. The second derivative is positive. If the curvature is concave. If your curvature is convex, then your second derivative will become negative. If it is a first derivative, it will find out whether it is a minima or maxima. So, since we go for the second derivative in the Laplacian, if we get a positive result, we say the curvature is like a concave, and negative result will reflect the converse curvature. In most of the situation, we have the two-dimension operator, which can be extended for three-dimension also. It reflects the local minima and maxima if V is positive. If the first gradient is negative, then it is a the point which we considered as the maximum value compared to the surrounding average value. So you can see the point we consider is E. If we get the first derivative as positive value, we can say the E value minimum is very much minimum than the surrounding average value. So Laplacian can also be 0, del square V equal to 0. Then we can say the particular this scalar field V is said to be harmonic, and this is a special case in the Laplacian, and this equation is also known as Laplace equation. Which I already stated, the Laplacian can be operated on both scalar as well as vector. If it is operated on scalar, then it is called scalar Laplacian. If it is operated on vector, then it is called vector Laplacian. Let us see the scalar Laplacian. The Laplacian of the scalar field V, here V is representing the scalar V, can be written as del square V, which we can say it is the del dot, which is the divergence of gradient V, can be also expressed as the divergence of gradient V, which is called del square V. So divergence of a vector is scalar, and del V, gradient of scalar, is vector. Since it is a gradient operator, it will result a vector. This vector is operated with a del vector, and it is doing divergence operation. Hence, finally you get a scalar product, which is del square V. The Laplacian of a scalar field is scalar. We can do a problem for scalar Laplacian. Here it is an f, it is a function of x, y, z, and is expressed in the equation x y square plus z cube. So del square f equal to, we say dou square by dou x square f, dou square by dou y square f, dou square by dou z square into f. Instead of function f, if you substitute x y square plus z cube, first time we have to differentiate with respect to x. So if you differentiate with respect to x, it goes 0, you get y square. On second time differentiation, you get that 0. Likewise, you do for the y also. So dou square by dou y square, you had first time differentiation, it will give 0, and this one will give 2xy, and second time differentiation it will give 2x, and this is for z square z, and the first time differentiation is 0 plus 3z square, and second time differentiation is 6z, so 2x plus 6z. So I'm going to the by doing the previous problem, try to solve these Laplacian operation. First scalar, we solve the first scalar operation. You do it, and in this video there are so many exercise problems will be there. You have to complete all the problems, and it should be submitted to you in the classroom. And also you do for this one also. Here R is this function is a this is a function in terms of R, and here R is equal to square root of x square plus y square plus z square. Now the Laplacian of scalar field can be written as del square f can be written as del dot del of, which we can say divergence of gradient f. So for initially they are doing the gradient, then divergence operation is performed. So we get this one. So likewise you do if also here what they is, they did the gradient operation. The gradient operators are given here. So for getting the Laplacian, you have a divergence of del dot with the gradient. So vector Laplacian, the scalar Laplacian operator is applied to vector field. It acts on each component in turn, generates a vector field. For understanding purpose, let us see a vector. We can see here f, it is a function of I, j, k, 3z square I vector plus x, y, z, j vector plus s square, z square, k vector. If you do the performing the del square operation, the del square operation will be performed by for this component, and for third component also. So let us do one by one. Let us take the first term, del square 3z square means, so del square itself have three components, x square, y square and z square. Since it is with respect to x, this time it goes 0, here 0, and this is with respect to y, so once again 0. So this one 6 is the first time, 10 second differentiation will be 6. Likewise second term also performed. With respect to x we get yz, with respect to yz once again differentiation 0, y xz once again 0, z xy second term differentiation 0, so totally you get 0 for the second term. And for the third term, del square x square into z square, so first time differentiation 2x z square, and second time differentiation 2z square. So this one there is no y component, so this one will become 0, z square, so 2x square z, and this time h2x square. So you get this as answer. So then you substitute for this, instead of this term you substitute as 6i vector, this component 0j vector, and this component will be 2z square plus 2x square into k vector. So totally you get the vector I and k component with j component as 0. So we can see if the Laplacian is operated on a vector, you get a vector result. So likewise you do the problem for this one and choose the answer, solve and choose which one is right. And in this problem you have to do the Laplacian, and after doing the Laplacian substitute the value 1 minus 2 1 and find out your answer. This is also you have to solve, and for the point you have to substitute 1 1 pi, for x 1, for y 1, for z it is pi. So do all these Laplacian problems, and here Laplacian can be expressed in cylindrical coordinates as well as spherical coordinates, and this is a Cartesian coordinates. For cylindrical coordinates you get this equation, and for though here you can see dou rho square, dou pi square and dou z square. For spherical coordinates dou r square, dou theta square and dou pi square you can do for this one. So we have some properties for Laplacian. So del square A can be easily written as divergence of we can write it as divergence of gradient operator or gradient of divergence. Gradient of divergence minus curl of curl A. Can be stated in certain cases. By using this identity, we can solve the problem easily. So del square A can be called as divergence of gradient of divergence minus curl of curl A. So only for the Cartesian coordinate system we can express this equation ax, ay, az. For Cartesian alone this will work out. So for differential operators, that means del operators, we have 4 videos, and let us have the summary of all the 4 videos. With the help of the del we can have gradient operation, divergence operation, curl operation and Laplacian operation. So gradient operator, when it acts on a scalar, the resultant will be a vector. It always acts on the scalar quantity. See, the gradient will always act on the scalar quantity. It is represented here. When it acted on the scalar quantity, it will give a vector. Divergence, when it will always operate on vector and the resultant will be a scalar. Curl also always operate on the vector field and the resultant will be a vector. But the Laplacian has two special cases. It can operate on scalar as well as vector. If it operates on a scalar, the answer will be scalar. If it operated on a vector, the answer will be a vector. So the formula will be for gradient del into pi, for divergence del dot v some vector, for curl del cross some vector, for Laplacian it is a del square some scalar quantity pi or del square some vector quantity v. In this last row, pi represents the scalar and v represents the vector. So I think you understand very well. If you have any doubt, you can ask me.